Roger here. Today we're going to be talking specifically about air tightness in buildings. We're going to cover four main things. Firstly, we're going to talk about why it's so important. The second one is why it can be actually quite dangerous to go air tightness without the right strategies. Thirdly, we're going to look at the trends over the last 20 years within the Australian building environment, see how it's changing and improving. And fourthly, we're going to just look at how we can do it better and make sure that we get optimal performance out of our homes every time. So why is air tightness so important? Well, there are a couple of main factors. The first one is to do with comfort. It's to do with the ability of the home to capture and maintain comfortable levels of temperature internally without using too much energy. So air tightness does this by ensuring that the air doesn't move between inside and outside, because air carries energy with it. We want to stop that from happening. So if you ever felt drafts in your home, those drafts feel really uncomfortable. They're also sucking the energy out of the building. So we want to stop that happening. If we can do that, we can also control how much energy we need to put into the building to replace what's being lost through those drafts. Second part of it is outside air contaminants. So we've got things like particle matter, we've got pollen in the air, we've got bushfire smoke, we've got carbon monoxide, radon gas, lots and lots of different things in the air externally, including noise. And all of those things are airborne, right? So if we can stop that air from outside traveling through our building fabric by making it more airtight, we actually protect ourselves inside the house and stop those things from harming our health. So that's why it's so important, and it's what makes a really good quality building, is maintaining that airtight barrier. So that all sounds great, but there's another part to it. It's also quite dangerous if it's not dealt with in the right way. You see, if we make our buildings really airtight, we're actually capturing a lot of moisture inside of the home itself as well. So we need to have a strategy in order to manage that moisture. So moisture from things like having showers at home, just breathing out generally creates moisture. Cleaning, just general life within your home creates a lot of moisture. And if that isn't exhausted from the building in a controlled way, it goes into the building fabric itself. And that creates condensation and eventually will create mold. And the biggest problem with this is most of it is hidden within the building fabric itself. You can't actually see it. And therefore, it's really, really dangerous because you don't know that it's harming your health and also harming the building fabric over time and degrading it. So we need to ensure that that doesn't happen. And the way we do that is by adding a ventilation system that actively works with you to ensure that those contaminants like moisture and others are exhausted from the building without you having to open windows and doors. So if you're going airtight, you must have these active systems in order to manage the air and moisture in the building. So next we'll look at the trends. And luckily the CSIRO have done lots of research on this recently. So we'll just have a quick look at the modeling they've done and get the results from that. Okay, so here is the article from the CSIRO, which is reporting on the research done by themselves about air sealing of homes and what they've found through testing. So they've tested 275 homes last year, and this report came out 2024. And so the key points, just highlighting here, so the research found that new Australian homes are actually 50% more airtight than those tested 9 years previously. So that's great news generally. The quality of construction is improving considerably, and 50% increase is pretty dramatic. The next one was the increase in your home's air tightness is a simple and affordable way to lower energy bills, increase comfort, and improve air quality. So that's what I was previously talking about. This just makes good common sense to go down this road. And it also says that poor air tightness can cause drafts, increase energy bills by up to 20%. We'll show you in our modeling that we can get a lot better improvement than 20%. And so, yeah, I'll get to that in a moment. But here is the warning. Overly airtight homes without controlled ventilation can lead to condensation and mold. Okay, so that is the issue highlighted right there by the CSIRO. So the test itself, so what they did, as I said, the whole report is in here, so feel free to go onto the website and have a look at this, and I'll post the link to this in our comments section, so you can do a bit more research yourself if you would like to do so. So yeah, the person who did it was the senior experimental scientist, Mr. Michael Ambrose. He was the person involved, and they tested them by doing this. They put this lower door system into 275 homes, and they pressurized the homes to a pressure of 50 pascals. And then they read how much air is leaking out of the building using this piece of apparatus. And their findings were quite interesting. So what they found is that air leakage is found in most new homes. So this is since 2015, with an average permeable rate of 6.9 meters cubed per hour meter squared at 50 pascals. So basically what it's saying is that at 50 pascals, which is the air pressure that they're putting into it, there are 6.9 air changes per hour. Okay. So the common leakage points are, poorly sealed exhaust fans, missing window and door seals, and leaks through heating and cooling ductwork. Those are the most predominant things that we need to look at in order to fix air tightness. But there's a whole strategy really that needs to be looked at from all of the architectural design and construction process to get this right. Interestingly, it said that older homes, and this is homes before 2015, are often around 30 air changes at 50 pascals. So that is huge. They're saying that's the equivalent to changing all the air conditioned air in the home every 40 minutes. So you can imagine every 40 minutes you heat up your home to a nice temperature, and then it just gets dumped back outside, and you have to replace it again the next 40 minutes, 100% of that conditioned air. So that is a lot of energy that you're having to reuse to get the building comfortable again. Okay, so let's just have a look at the difference between the standard Australian home and a passive house. So this is what's called the PHPP, which is the Passive House Planning Package. And this is the design tool we use to understand if a passive house is meeting the criteria. And this specific portion of the document here is called the verification page. And this is where we get all the checks to ensure that we're actually achieving the passive house standard. And in order to do that, the building proposed needs to meet a whole series of criteria. And one of those criteria is air tightness. So air tightness in a passive house needs to meet the criteria of 0.6 air changes per hour. And that's at 50 pascals, which is the same metric that the CSIRO used, 50 pascals of air pressure. They had an air change of the average house in Australia achieving 6.9 air changes per hour. In passive house, it's 0.6 air change per hour. Okay, so that's what's making us this building work so well. What I wanted to do is just change this so that this was the average building in Australia, just so we can see what effect that has. Okay, so we're going to just change the metrics here. So now we've got our criteria is 0.6, but our building is actually achieving 6.9. So this now is the average in Australia over the last 10 years. Okay, so now we can see we've got a big no up here in this area. And this area is to do with the space heating requirements for the building. So if we look across here, we can see the criteria. So the criteria is either one of these two. So we can have the heating demand, and the heating demand of the building is the amount of heat required to maintain a comfortable temperature range. Okay, so the comfortable temperature range typically is 20 degrees, and we want that nice and average throughout the building throughout the year. And that should rate at 15 kilowatt hours per meter squared per annum. But this building now, the average Australian building, is actually almost double that at 28. So we're actually not achieving this criteria. We're actually twice as bad as a passive house. The next part of it is heating load. And so heating load is to do with the power the heaters need in the building to maintain that comfortable temperature of 20 degrees on the coldest day of the year. So they're saying that it should be no more than 10 watts per meter squared. Okay? So we're now saying that this is not 10, this is 27. So it's almost 3 times as much energy, and those heaters are requiring to heat the building up. So this building is using almost 3 times as much energy to heat itself to maintain the comfort level. Now, I didn't change any other metrics apart from the air tightness of the building. This building has still got really, really good insulation. It's still got really, really good windows and doors. It's still got a mechanical system that's filtering and removing the contaminants inside and making sure that that energy is being recovered. It's making sure that the building also has no thermal bridges through the envelope that's sucking the energy out. The only thing we changed was the air tightness. And so you can see what a big difference this has. By just going to the average building, we are using 3 times as much energy to heat the building up to maintain that level. So that is why passive house is so powerful, because air tightness is not actually that difficult to achieve. It's just a process that we have to go through in the design, and then it needs to be tested and checked on site to ensure that these standards are actually being met. And so this is how we do that, and this is how we make sure we're actually achieving the standards and making better buildings for everybody. Hope that makes sense and it's not too technical. If it is, yeah, shout out in the comments. Let me know if you've got any questions. I'm happy to provide some more detail on this or do another video that will answer some of these specific issues that you might be having in understanding this. So there you have it. You've got now a clear picture of why airtightness is so important, why it's dangerous if it's not controlled in the best possible way, what the trends in airtightness have been recently, and also we've been looking at passive house modeling, and that is how we make buildings better. We do it through lots of really good quality modeling, and most importantly, we then test for airtightness on site using a blower door test. But it's most important of all things is to not look at airtightness as isolation. It's got to be part of the bigger solution. It's got to be dealt with in regard to the ventilation systems. It's got to have a good quality insulated building envelope that is ensuring that it's not leaking the energy out of the building as well. need to ensure that there are no thermal bridges through that structure that are sucking the energy out through the building and potentially causing risks to condensation and moisture buildup. And finally, we need to ensure that the windows and doors that we put into our building are equally as good performing as we can find anywhere in the market, because they are often the weakest points thermally in the building, and ensuring that they're well taped to the building envelope to maximize air tightness. So air tightness is a big plus, but let's do it in the right way. Thank you so much for listening. I hope you learned something today. Leave us a comment if you want some more information, and yeah, I'd love to hear about what you're doing to actually maximize the air tightness and energy efficiency, comfort and health within your building.